Cylindrical pressure vessels, hydraulic cylinders, pipes carrying fluids at high pressures develop both radial and tangential stresses that depend on the radius of the element being considered. In order to calculate the tangential stress sigma t and radial stress sigma r, we assume that the longitudinal elongation is constant around the circumference of the cylinder. And they can be calculated by using these following equations. Ri represents the inside radius of the cylinder. Ro represents the outside radius of the cylinder. Po is the external pressure. Pi is the internal pressure. And by substituting the values, we can calculate the tangential and radial stresses as follows. If the external pressure Po is equal to 0, they take the following form. And the distribution of the tangential and radial stresses are presented on the right side. When the wall thickness of a cylindrical vessel is about 1/10 or less of its radius, the radial stress resulting from the pressurization is quite minimal in comparison to the tangential stress. In this case, the tangential stress can be determined as follows. Here, P represents the internal pressure acting on the wall of a cylinder of thickness T, and the inside diameter of the cylinder is represented by di. We can use the following formula here to calculate the average tangential stress. Sigma T average is equal to PDI divided by 2T. And by using this equation, yes, we can calculate the average tangential stress regardless of the wall thickness. And for a thin walled vessel, we can also perform an approximation to calculate and determine the maximum tangential stress. In this case, sigma T max, which represents the maximum tangential stress, is equal to P times di plus T divided by 2T. Here, the di plus T represents the average diameter. If the both ends of the thin-walled vessel are closed, in this case, the longitudinal stress exists because of the pressure acting on the ends of the vessel. And in this case, we assume that the stress is uniformly distributed over the wall thickness, and we can easily determine the longitudinal stress sigma L by using this following equation. Sigma L is equal to PDI divided by 40. A rotating ring is a rotating element such as flywheel, blower, or a disc. The type of the stresses occurring in rotating rings are the tangential stresses and radial stresses. These tangential and radial stresses are similar to thick-walled pressure cylinders, except they are caused by inertial forces. And we can calculate these tangential and radial stresses by using the following equations, but we need to follow these restrictions here. The outside radius of the ring or disc is large in comparison to its thickness. Actually, it is larger than 10 times thickness. The thickness of the ring or the disc is constant, and the stresses are constant over the thickness. And then we can calculate the tangential stress, sigma T, and the radial stress, sigma R, by using these following two equations. Here, R represents the radius of the stress element under consideration, rho represents the mass density, omega represents the angular velocity of the ring in radians per second, and if we are analyzing a rotating disk, in this case we use Ri equals to 0 in these equations. When two cylindrical parts are assembled by shrinking or press-fitting one part upon another, there will be some contact pressure developed between these two parts. And when these two cylindrical parts are assembled with a radial interference of delta, this contact pressure, the pressure at the interference, can be determined by using this following equation. I represents the properties of the inner member, O represents the properties of the outer member. If they are made of different materials, EO represents the modulus of elasticity or elastic modulus of the outer material member. EI represents the elastic modulus of the inner member, and here mu represents the Poisson's ratio. For example, nu O represents the Poisson's ratio of the outer member, nu I represents the Poisson's ratio of the inner member. If these two members are of the same material with the same material properties, naturally, in this case, the first equation can be simplified into the second one as follows. When the temperature of an unstrained body is increased, there will be some thermal strains developed inside the material since the body expands. Why? Because please recall the definition of strain. Strain is deformation per unit length. When we increase the temperature of the object expands and there is some deformation. Therefore, there will be some strains developed inside the material. The type of the strain is the thermal strain. And we can calculate this thermal strain in x, y, z directions by using the following formula. Epsilon is equal to alpha times delta t. Here, alpha represents the thermal expansion coefficient. Delta t represents the temperature change in degrees. And if the body is restrained, for example, if we have a straight bar which is restrained at both ends, in this case, there will be also some stress, compressive normal stress developed inside the material. And this compressive stress can be calculated as follows. Sigma is equal to negative epsilon times E. Epsilon represents the thermal strain. E represents the modulus of elasticity. We put a negative sign here in front of the stress since the type is compressive stress. If we are analyzing a straight bar which is strained at both ends, for example, if we clamp the both ends of the straight bar, in this case, there will be some thermal stress, compressive thermal stress developed inside the material. And this normal stress is also equal to negative alpha times delta t times E because we replace this epsilon by the corresponding equation alpha times delta t. Yes, as I indicated before, if the bar or the object is unstrained, in this case there will be only thermal strain developed inside the material, no stress. But if the object is restrained, in this case there will be also some thermal stress developed inside the material. If we are analyzing a uniform flat plate which is restrained at the edges and subject to the uniform temperature rise, the compressive stress developed inside the material can be expressed by using the following formula. In this case, we are dividing the compressive stress by 1 minus nu. Nu represents the Poisson's ratio of the material because naturally this uniform flat plate is made of a material. Both of these equations are called thermal stresses, and thermal stresses only occur if the structure is restrained. Otherwise, there will be only thermal strains developed inside the material. When two bodies having curved surfaces are pressed together, there will be some stresses developed in these two bodies, and these stresses are three-dimensional. For example, contact stress problems can occur in the contact of a wheel and the rail, and also in the action of rolling bearings. We should analyze these contact stresses because typical failures can be seen as cracks, pits, or flaking in the surface material. We will first analyze the spherical contact stresses. For this purpose, please see this figure here, you can see the contact stress distribution. As you can see, it is hemispherical. Let's assume that we have two solid spheres of diameters d1 and d2. These two solid spheres are pressed together with a force of F. In this case, a circular area of contact of radius of A is obtained. And we can calculate this contact of radius of A, the radius A of this circular area of contact, by using this following formula as a function of material properties of the first and second sphere. F represents the applied force, nu1 and nu2 represents the Poisson's ratio of the first and second sphere, respectively. E1 and E2 represents the modulus of elasticity of the first and second sphere, respectively, and as I indicated before, D1 and D2 represent the diameters. The pressure distribution within the contact area of each sphere is hemispherical, as presented in this figure, and the maximum pressure occurs at the center of the contact area. And we can calculate this maximum pressure by using this following formula. P max is equal to 3F divided by 2 pi A squared. The magnitude of the stress components below the surface as a function of the maximum pressure of contacting spheres are presented here in this figure. Please note that the maximum shear stress is below the surface at Z equals 0.48 and its value is approximately equal to 0.3 Pmax. This chart presented here is based on a Poisson's ratio of 0.3. Please also note that all of the normal stresses which are presented on this chart are compressive stresses. We can now analyze a similar situation in which the contacting elements are two cylinders of length L and the diameters of D1 and D2 as presented in this figure. The area of the contact is a narrow rectangle of width 2b and length L, and the pressure distribution is elliptical this time. The half width b of this narrow rectangle can be determined by using the following equation. And F represents the applied force, nu1 and nu2 represents the Poisson's ratio of the first and second cylinder, E1 and E2 represents the modulus of elasticity of the first and second cylinder respectively, and D1 and D2 represents the diameters of them. The maximum pressure can be determined by using the following formula. Pmax is equal to 2F divided by pi BL. And the magnitude of the stress components below the surface as a function of the maximum pressure for contacting cylinders are presented here. The largest value of the shear stress tau max occurs when Z over B is equal to 0.786 and its maximum value is equal to 0.3 Pmax. This chart is based on a Poisson's ratio of 0.3. Please note that all of the normal stresses presented in this chart are compressive stresses.